Second half of this session. Just as a reminder to everyone, we're going to be having 4 separate videos played here. The first one is going to be Alexandra Navrotsky's presentation. Then we're going to be seeing an NSF video produced for the Navrotsky group. And then Sergei Ushkov will be talking a little bit more about different calorimetry techniques and high temperature in situ diffraction. And then finally, we'll be hearing from Axel van der Waal again at the end to finish off this session. So with no more further ado, Alex will begin for us.
Thank you very much for continuing to listen. The second half of our presentations will emphasize experimental techniques, particularly for high temperature calorimetric and differential scanning calorimetry and X-ray measurements. So my talk then is on advances in calorimetry for refractory materials and look at what CalFAD needs. So CalFAD needs definitely enthalpies and entropies of formation of materials, heat capacities from near 0 Kelvin to melting and in the molten state whenever possible, thermodynamics of phase transitions. This means first order phase transitions, second order phase transitions, disordering transitions, determining what transitions are true stable transitions, what transitions are the evolution of metastable phases, thermodynamics of mixing in solid solutions and in melts, melting points and heats and entropies of fusion of high melting materials. The data for oxides is reasonable but still incomplete. The data for carbides, oxycarbides, nitrides, etc. is very fragmentary and largely absent. So we need experiments to complement and test computations. We need computations to both test and direct future experiments. And I will review then high temperature calorimetric methods and give some examples of things that we have done in the decade or so of our collaboration. So high temperature oxide melt solution calorimetry is the first and major technique that we use in my group. This is in a way the signature methodology of what was the Peter A. Rock Thermochemistry Lab at Davis and now is Thermo2, the Thermochemistry Lab at Davis. At Arizona State. We dissolve oxide samples, typically 5 to 15 milligrams, sometimes less, in a molten oxide solvent, typically 20 grams, to form a dilute solution which follows Henry's law, so we do not have to worry about the concentration dependence or the interaction of species in the solution. The differences in heat of solution of reactants and products gives the heat of reaction. Oxidative reactions for nitrides, sulfides, selenides, carbides, etc. have been and continue to be developed. And these calorimetric methods are needed for ceramic and refractory materials which do not dissolve in aqueous solvents. After all, if we deal with rocks and thermally stable materials, getting them to react is a necessary first step. The calorimeter itself, and this is our new calorimeter here at ASU, is based on calorimeters that we have built in our laboratories, but now it is commercialized as the Ceterama Lexis calorimeter for solution calorimetry in molten salts and other applications. And a number of groups in the United States, Europe, and elsewhere have now bought these calorimeters, and I'm proud to say that they are getting independent of me in planning and doing experiments. The calorimeter itself is a heat flow calorimeter in which a sample chamber is surrounded by a thermopile. The small temperature difference drives heat flow, and we get a calorimetric peak which is proportional to the heat effect. The experiment itself consists of dissolving the sample by dropping a small pellet into a melt. We often stir the melt and control the atmosphere by gas bubbling. And the accuracy that we typically get is on the order of between 0.5% and a couple of percent in the heats of solution, and therefore a few tenths to a couple kilojoules per mole in the heats of reaction or heats of formation. choosing the proper molecular weight for comparing materials is something that one has to pay attention to. As an example of some of the work that we've done, we have worked extensively on fluorite structure-derived oxides. These are superstructures based on the fluorite type, and these superstructures include pyrochlore structures, Weberite structures, and in some cases, disordered fluorite materials. We have looked at the enthalpies of formation from the oxides as a function of the rare earth, and we see fairly consistent trends that the materials with larger rare earths are more stable than the materials with smaller ones. And the slopes of these lines then give us some predictive capability for the future. Heat capacity measurements, cryogenic or adiabatic calorimetry, or calorimetry using the PPMS system from quantum design, allows one to obtain standard entropies, let's say S0298 of materials. High temperature differential scanning calorimetry or enthalpy increments by drop calorimetry can get us heat capacities above 1200 degrees. Lower accuracy is obtained, of course, at higher temperatures. The difference in CP between phase assemblages in the solid state, especially at high temperature, is reasonably constant and reasonably small, so the assumption that we don't have to worry too much about the high temperature heat capacities is reasonable. We do have to worry about the low temperature heat capacities. Here is an example simply of a measured low temperature heat capacity by my colleague Brian Woodfield at Brigham Young University on the thermodynamics of Syria containing neodymium oxide as a dopant. This was done for other reasons, but the point of showing this curve is that whereas at high temperature, the heat capacity varies approximately linearly with composition, at low temperature it does not, and in fact, as T approaches zero, the heat capacity has to approach zero at zero with zero slope. That is, it has to become horizontal, approaching zero. One cannot calculate what these parameters would be from high temperature heat capacities alone. One cannot extrapolate from high temperature to low temperature. One needs the measurements. In some cases, one can do computations of these low temperature heat capacities, but fundamentally one needs the measurements to obtain entropies of phases at 298 Kelvin, and then one can correct entropies, heat capacities, enthalpies to higher temperature using the DSC result. We can extend these heat of solution measurements to much higher temperature using a commercial Ceteram MHT96 system. We use it fundamentally in dropping mode, in which we drop samples into a solvent in a hot calorimeter, but now at a temperature of, for example, 1450 degrees centigrade instead of 700 or 800. The accuracy is smaller, but being able to get heats of solution, heats of formation, heats of reaction within silicate melts using the calorimeter as an instrumented magma chamber is really an exciting new development. As an example, we have heats of solution of a number of oxides in a slag in the calcium, magnesia, alumina, silica system. And the point really is that we get very reproducible results within a few percent. We get some scatter in the results, particularly when we have iron oxide materials. But this shows then that this is a evolving and developing technique, and we have plans for the future to look at a number of rare earth oxides in melts of different composition. It is, of course, the structure on the atomic scale of the molten state that helps determine the heat of solution. Getting to differential scanning calorimetry or thermal analysis in general, certainly there are many calorimeters for work up to 700-800 degrees C, but our interest in high temperature materials is taking these techniques to much higher temperature, and we can in fact go to about 2500 degrees C using, for example, the Ceteram Setsis TGDTA system, which we have reprogrammed so that we can actually go up to probably about 2500 degrees C. What we do is encapsulate the sample, typically in tungsten, because in fact the graphite furnace, for example, will cause a lot of carbon contamination. And keeping the sample separate and non-reacting with the container is a major challenge at high temperature. Not a challenge that you can overcome completely, but a challenge that you can minimize by good experimental technique and sometimes some tricks. So we have measured various heat capacities. We need to calibrate these DSCs. They are, after all, just like any other differential scanning calorimeter. You don't get an absolute value of heat. You need to do a calibration. So in this strange world of high temperature, the highest material in oxides for which the heat of fusion is well known is aluminum oxide, and we have used that as a calibrant for our high temperature DSC. But we soon realized that we cannot extrapolate those values very well to even higher temperature, and we sought other materials, perhaps yttrium oxide, that melt at higher temperatures as calibrants, and we saw inconsistencies in published data, an interesting realm perhaps for CalFAD, that made us think we needed to remeasure some of these materials at high temperature, and led to the ability to quantify these results once we have a calibration. And here then we have phase transitions and melting of neodymium oxide. The point is that these look like very nice DSC peaks. They are in fact reversible, and we see two small phase transitions among solids from the low temperature A rare earth oxide phase to a hexagonal phase to an X phase to melting. The heat of fusion is, of course, bigger than the heat of the phase transitions, which is reasonable, and we measure temperature either by a thermocouple or by a pyrometer, and we have a little bit of questions of what the temperatures, how well we can control the temperatures. The right-hand side of the slide just shows the occurrence of different structures in the different rare earth oxides, and we're still working on a number of them. So I said that we needed to calibrate our calorimeters. This was part of the impetus of building a drop calorimeter. That is a calorimeter that drops a sample from high temperature into a calorimeter at room temperature and measures the heat content. Above the transition, the heat content includes melting. Below the transition, it does not. This has been done with very large samples on large calorimeters in the past, although probably none of these systems are operating anymore. We have taken this in a different direction, namely to use containerless melting, to use a levitated sample heated with a laser above a very small calorimeter, and to drop that sample into the calorimeter to measure its heat content. And to do this, then we need very good control of the sample geometry, the sample temperature, the calorimetric process. And indeed, we still have some issues we need to solve, particularly in terms of the temperature distribution in the sample. Nevertheless, we are now getting accurate data. For example, we get the heat of fusion of aluminum oxide, and this is just a normal enthalpy curve. The drop in enthalpy between the melt and the solid is, in fact, of course, the enthalpy of fusion. And we now have measurements for yttrium oxide, show a little bit of temperature dependence for various reasons, but we still get an enthalpy of fusion that we then can use to calibrate our DSC. So the conclusions and outlook on this, then, is that calorimetry of refractory materials at high temperature is growing in both quantity and quality. Quantity in terms of the number of laboratories working on it, quality in terms of improved calorimeters, calorimetric techniques, and chemical knowledge. One needs a systematic approach to obtaining the data and creating useful databases in CalFAD or elsewhere for phase diagram calculations. And the question is, we need new databases, and Sergey will be talking about databases for thermal analysis, because the sort of data one gets of thermal analysis is slightly different in format from the data that one might get for measurements of heats and entropies. And indeed, to introduce some of the things we'll be talking about, is that once more, one wants a database based on experimental thermal analysis data to then be able to use for the prediction of many reactions of interest in both fundamental science and technology. Thank you.
I would also like to remind all the attendees is that if people have questions for Alex, to add them to the Q&A, and then we'll address those questions at the end of this section. So next, we're going to watch a short video that was put together by the NSF, focusing on the drop and catch calorimeter.
So we're at about 2,300 degrees for the surface temperature.
For Matthew Fiery, the heat is on. This little bead is made of what's called a rare earth oxide. It's a high temperature material.
High temperature materials, very loosely speaking, are materials that are like rocks. Nothing much happens to them until you heat them up.
With support from the National Science Foundation, chemist Alexandra Navratsky and a team at the University of California, Davis have built this instrument to study the structure and stability of rare earth oxides when they reach their melting point. That's when chemical reactions can start to take place.
All the interesting things that happen in terms of their thermodynamic properties, in terms of their changing from one structure to another, occur at temperatures at white heat and above, let's say 1,500 degrees centigrade.
Rare earth oxides are a key component in many electronics. Cell phones, batteries, lights, medical scan machines, and many more devices all contain these relatively poorly understood elements.
We have erbium, lutetium, thulium, ytterbium, neodymium, we have yttria, we have, oh geez, I should be able to name all of them.
They begin their study of the rare earths by making them into little beads.
The problem is at high temperature, everything reacts with everything. How do you overcome that problem? You try to make a sample such that it's not in contact with anything other than the inner atmosphere. How do you do that? You levitate a sample.
The technique is called drop and catch calorimetry. They levitate a bead, zap it with a laser to melt it, and then drop it.
And so what happens is that the bead is heated up here and it falls, and then we just, like that.
As the bead solidifies, sensors behind those copper plates measure heat flow and a property called heat of fusion, how much energy it takes to melt the material.
If you want to calculate how many different materials interact with each other, you do this by a series of theoretical calculations, and these properties of the melting have to go into that.
Navratsky says insights gleaned from this work could have applications for nuclear waste storage. Rare earths are a byproduct of nuclear fission. Also, the aerospace industry, in the form of new heat-resistant materials for spacecraft, and also improved coatings for aircraft engines to keep them from overheating.
We've built it and we are still improving it little by little. Eventually, perhaps it will get commercialized, but right now it's a prototype, and as far as I know, we're the only ones that have anything like it.
Matthew Fiery helped develop this instrument as an undergraduate. For him, breaking new scientific ground has been a revelation.
Honestly, when I first realized it, I just kind of sat there for a minute just being like, this is magic. Because through the development and work of others, all those generations, you kind of feel like, I don't know, I guess I get kind of philosophical on it. You actually feel like you're a part of a grander movement, something that's really important and bigger than yourself.
Alex Navratsky can appreciate his enthusiasm. She's been a chemist for more than 50 years, a leading one for much of that, a pioneer for sure, but an unassuming one.
Basically, I just, went my own way and did the things I wanted to do and perhaps surprised myself, look where I am. Only in retrospect do you realize that you were a pioneer. It's all in a day's work.
Going to extremes, probing the properties of high-temperature materials, unmasking the mysteries of rare earth oxides. For Science Nation, I'm Miles O'Brien.
Okay, so next up, we have Sergei Ushkov's presentation. But before I play that video, I'd like to introduce Sergei. So Sergei Ushkov is an associate research professor at ASU's Center for Materials of the Universe. He completed his PhD in mineralogy at St. Petersburg State University with Professor Valdemir Kurvovichev and worked at the Copeland Radium Institute in Russia. He joined Alexander Dovrotsky's group in UC Davis in 1999 as a postdoc and continued as a staff research associate. He was responsible for developing new experimental approaches for measurements of surface energies, ultra-high temperature calorimetry, thermal analysis, and X-ray diffraction. And so here is Sergei's presentation.
Hello everyone, my name is Sergei Ushakov, and since my talk is right after the movie, I decided to add a first slide with a closing credits listing all the people who helped us to build our laser system and make drop calorimetry great again. Also, many of the same people were involved in their high temperature diffraction, which I'm going to focus in this talk. The subject of my talk today is CalFAT inputs from high temperature diffraction, CalFAT and thermal analysis databases. I'm going to talk about diffraction above 2000 C with focus on rare earth oxides, zirconates, and hafniates. I also want to use this opportunity to bring the subject of thermal analysis databases. Now, there are essential inputs from high temperature diffraction into both experimental branches of CalFAT. That is, we can get the high temperature structure and thermodynamic on single phases, which not quenchable to room temperature, identify reversible phase transition, calculate configurational entropy on order disorder transitions from refining site occupancies, and they change with temperature. Also, volume change on phase transitions is also not used in current CalFAT. It's very helpful to compare with ab initio computations, because while cell parameters are known to differ from experiments, volume changes are much more accurate. Also, experimental phase diagrams can often be determined from very few compositions if you have their high temperature diffraction capabilities and some knowledge of the system. So in this example, you can see the shape of miscibility gap and liquidus and solidus identified from a single sample. Now, our involvement in high temperature X-ray diffraction actually started with CalFAT. This is the review by Matvey Zienkiewicz published in 2007 on thermodynamic of rare earth Sesky oxides. And the purpose of this review was the creation of their thermodynamic database, which he did, and which is now openly accessible at NIST materials data repository. So he finished the review with a question: does the cubic fluoride type structure represent the high temperature modification of yttria? Can the oxygen activity in the gaseous environment induce structural changes in yttria and other rare earth Sesky oxides at high temperatures? So going into yttria problem, room temperature structure of yttrium oxide is Biggs by its structure, similar to other heavy rare earth oxide. Yttrium ionic radius is between holmium and erbium. Melting temperature of yttrium oxide is actually well known and characterized by several techniques, and was suggested by IUPAC for use as a secondary temperature standard. It is also known that it has a phase transformation about 100 degrees before melting, which we can also see in DTA in our laboratory. However, there is still pending question about its high temperature structure. Foix and Travers first studied yttrium oxide together with other rare earth oxides and reported that it has an H-type structure similar to holmium and erbium at high temperature. Now, Katagiri in Japan reported that he quenched fluoride-type yttrium oxide by laser heating yttrium oxide rod in unspecified gas atmosphere. And that report was similarly confirmed in 1999 by Swami, who reported fluoride-type structure from high-temperature X-ray diffraction measurements. So I have seen that yttrium oxide in fluoride structure is used in recent Kalfat optimizations and in zirconia yttria system. And I understand because it's very convenient since high temperature structure of zirconia is accepted to be fluoride structure. However, we want to find out what is the real structure. Bixby structure is often described as a defect fluoride structure in which vacancies are ordered. So possibility that it is a high temperature structure or at least a transient structure is very real. And first we try to reproduce Katagiri results by quenching yttrium oxide from melt or annealing it at high temperature with a laser. However, we were always getting Bixby structure. So we started to look into high temperature diffraction. So classic method of high temperature diffraction is using capillary heated either with resistive heating or with image furnace. And these setups were available at the synchrotron. However, you cannot go above 2000 C due to aluminum melting temperature. Now, the strip heater can be used to the higher temperature depending on the material. And actually, that's how yttrium oxide was identified as a H-type structure by Foix and Travers in 1966. They used a rhenium strip heater in helium atmosphere. And Swami as well used tungsten wire in argon in his high temperature diffraction measurements. Well, now looking at his data, however, you can see that his report was heavily influenced by Katagiri communication about quenching fluoride type yttrium oxide phase, because these peaks Swami attributed to fluoride phase can also be interpreted just as resulting from a sample displacement in his experiments. Of course, the use of strip heater is limited to inert atmosphere if you're interested in the temperatures above melting point of platinum. Aerodynamic levitation doesn't have this limitation. And it turns out it was used on synchrotron to study structure of oxides since 1997. However, it was a structure of liquid oxides. Now, aerodynamic levitators with laser heating are available in user program at Advanced Photon Source, at Argonne National Lab, at Spallation Neutron Source at Oak Ridge National Laboratory. And they are operated thanks to the effort of Chris Benmore, a beamline scientist on 6IDD, and Jörg Newfind, who is one of the beamline scientists at Nomad Beamline, and Rick Weber, who built these levitators and providing constant upgrades. Samples for aerodynamic levitation are usually prepared by laser melting of powders. They naturally form spheroids due to surface tension, but exact shape will depend on volume change on melting. For study on structure of melts and glasses, stable levitation is usually achieved. However, to get the powder-like X-ray diffraction pattern, we need to rotate the sample, and usually it can be accomplished simply by adjusting gas flow through the nozzle. Mostly we were using synchrotron source, and data collection are very fast. You can get decent pattern in less than 10 seconds. With neutron, experiments are trickier and collection times are longer, but of course you can get very valuable information on the oxygen and on the thermal parameters. So we performed experiments on yttria almost 10 years ago, both in oxygen and argon, and we only saw H phase. Well, interestingly, by refining the patterns which contain both C and H type phase, we can detect a volume change on CH phase transformation, and it's negative. Later, in collaboration with Axel van der Walle group, we studied rare earth oxides, and we also see a negative volume change on the CH transformation and erbium and holmium oxide. It is about 3% reduction. This unusual volume reduction on high temperature transformation is not that unusual for rare earth SQ oxides. In fact, Biggs-by transformation to monoclinic B-type phase also accompanied by volume reduction, and all rare earth oxides can be synthesized in B-type phase under pressure. In 2008, there was a report on synthesis of H-type phase of yttrium oxide at the pressure above 24 GPa. However, it cannot be quenched. On decompression, the sample transformation to the B phase was observed, which can be quenched. After our first work on yttrium oxide, we used Levitator at APS for 3 more sessions and collected data for a number of compounds, mostly rare earth oxides, zirconates, and hafniates. We also did experiment on Levitator and NOMAD at spallation neutron source, and that was limited to lanthanum zirconate and yttria-stabilized zirconia. To summarize our findings, lutetium and ytterbium oxide maintain Biggs-by structure to melting temperature both in oxygen and in argon. In this case, we were able to refine atomic positions and thermal parameters to the melting temperature and correlate structural details and fusion enthalpies with computation. The rest of rare earth oxides, including yttrium oxide, transform to H and some to the X phases, characterized by fast oxygen diffusion and superplasticity. The structure of these phases is actually similar to liquid. For rare earth pyrochlores, we found that neodymium and lanthanum hafniate and zirconates retain some ordering up to the melting temperature. However, the rest disorder to defect fluoride structure. And Pardamaram was able to refine anti-site occupancies and calculate configurational entropy change for order disordered transition. We also correlated these results with differential thermal analysis data. For cubic zirconia and hafnia, we were able to refine volume change on tetragonal to cubic transformation, which is positive, and thermal expansion for the cubic phase to the melting temperature. We compared these results with computations, which also indicated that heat capacity of the fluoride high temperature zirconia and hafnia is similar to the heat capacity of the liquid zirconia and hafnia, which is not surprising because dynamic disordering of an oxygen sublattice also takes place in fluoride phase and yttria-stabilized zirconia, as we showed from results of the neutron diffraction style. At the end of my talk, I would like to bring a subject of CalFAT and thermal analysis databases. Of course, thermal analysis contributed greatly to development of CalFAT databases, first by providing data for single phases, such as heat capacity and enthalpies of transition and fusion, and then by determination of experimental phase diagrams. I think every CalFAT user well aware about thermal analysis. However, I don't think the reverse is true. There is a dozen of the companies which produce thermal analysis instrumentation and the software, and there are several national thermal analysis societies which hold regular meetings. So let's talk about what thermal analysis databases are available. The first effort on collection of thermoanalytical curves originated in Hungary, and 5-volume atlas was produced containing 400 inorganic and organic solids. And until very recently, that was all what is available. Recently, NICE changed this situation to the better and created the most comprehensive database in thermal analysis. However, for example, for metal alloys, it has only 143 entries. I think here is an opportunity for CalFAT to extend its user base by providing thermal analysis users with theoretical thermal analysis traces based on CalFAT computations. From other side, there could be some benefits in start feeding inverse pyramid of CalFAT from the top with thermal analysis data for complex compositions. Some of their scanning calorimetry data on complex compositions were collected by instrument on board on Phoenix lander on Mars in 2007-2008. However, there is no thermal analysis instrument on any of 3 rovers currently operating on Mars. So I would like to finish my presentation with the following message. Let's get thermal analysis back on Mars, and let's get it powered by CalFAT databases. Thank you.
So again, thank you, Sergey, for that awesome presentation. And if anyone has any questions for Sergey, don't forget to put them down in the Q&A. We have one last quick wrap up from Axel, and then that will shift us over to our Q&A session.
Okay, as concluding remarks, let me use this very well-known painting as a background. So we are talking about connecting models and the real world. So we've seen essentially what we've seen is that sometimes we can actually touch. The two can actually touch. And what do you need for that? Well, we need to make increasingly realistic simulations. We need to make increasingly ideal measurements. And if we work hard enough, eventually we actually agree. So in this talk, what we've seen is, on the experimental side, we've seen, very amazing efforts to remove all the imperfections that you could have imagined in measurements, removing the container through levitation measurements, being able to access high temperature properties using, laser heating, a lot of calibrations also that is needed to get all of these measurements to actually work out very well. We've seen some neutron diffraction, X-ray diffraction done at high temperature and under levitation. So all of these things contribute to making these measurements as clean as possible. And on the side of the modeling, well, we've had to essentially introduce defects. So we start with something very ideal, like a perfect crystal at 0 temperature, which never happens. And we have to add defects. We have to add, vibrational electronic contributions, configurational contributions. And even some things like, very advanced exchange correlation functionals are sometimes needed to even get the right result for high temperature. And even properties that you would think experimentally are very easy to get, like melting points, are actually at the extreme difficult level of difficulty in terms of getting it from computations. But thankfully, thanks to Kijun's methods, this is actually now fairly, feasible to do it in a systematic way. Now, I just want to remind you, though, that it's not that common that we can have materials property that we can both predict and measure and actually agree. If you look at mechanical properties, optical properties, or even just simple kinetic diffusion properties, this is very difficult to do. And what is really remarkable here is that for thermodynamic properties, we can actually make what we call a finger touch. We can actually have this agreement at the end. And of course, I have to apologize to our experimental colleagues that I depicted the model as the godly figure and the real world was the poor human. But at least I gave you the young body and I'm the old, man here. So anyway, I hope this is a nice way to summarize all of this. So thank you. We welcome your questions.
Looks like I cannot type questions. Maybe I can directly ask questions. That'd be good.
Yeah, so only attendees can ask questions in Q&A sessions. As
oh, okay, that's why I can
cannot.
have a question. I cannot do that. Okay, I have two questions. I want to Sergey. So one question is that where is Dr. Zinkwich now?
Well, Matvey is in Germany. Yeah, in Germany, working for a private company.
Okay.
We exchanged some emails with him and
okay, we do that. Please say hello to him. We had a joint paper back in 2006. Then I lost the connection with him after that.
Yeah, absolutely. I will send him the link for presentation.
Okay, okay. The second question is that you mentioned there's a thermal analysis database. I think it's very critical. Is anybody collecting them put together as a database now?
Well, that's what we plan to put together with Axel van der Walle and Chijin Hong. Yeah,
okay.
At the end
when you do that, I really encourage we work together, because we have this SBA using this data. We use the data in JSON format, but we plan to store the data in MongoDB database. I think we should talk about it, maybe with Alex too together. We can have joint efforts we have structured it already. We can work together to put the data. And we're also working on this, we call it NLP, natural language processing, can get the data directly into the MongoDB.
Yeah, absolutely. Yeah, of course, in some systems there are perovskites formed. Yeah. So we were so far we were focused on just pure earth oxides, but I think with the idea that with the computation Chujin does, I hope that we can get some high fidelity data and then just rely on the ab initio, the way it looks.
Well,
because they're so accurate.
As I mentioned, you always need experimental validated. You always need that one. So I really think there's a good opportunity for us to do that. And we really encourage maybe after the conference, we can set up a meeting to discuss further steps, how we do that. And then I think it will be huge importance to the community.
Yeah, absolutely. Thank you.
Thank you. And Axel, I know I discussed already on this instability issue. I think we save that one for the gather time discussing again. That's great discussion too.
That's right. Yes. Somehow the sound is so much better on Zoom, though it's easier to get the ideas across this way. But anyway, we can still talk about it later.
Okay. Fantastic talks. Thank you very much.
All right. What do we have? We still have more questions.
Yes, we have several questions that are coming through the Q&A. The first question is from Ursula. Would you be able to promote her so she can verbalize the question?
Yeah, so let me do that. Yeah,
I also promoted Natalie as a panelist. She raised up the hand. You can ask a question.
Okay. All right. So Ursula, you can share
yes,
your video
I
now.
just had to unmute myself. it's not so much a question, or maybe it's a question if somebody would be interested in reversing what we did with the DTA guide that Sergey showed. We wrote scripts to take Calfat enthalpies as input to generate DTA curves. So we were able to simulate certain scenarios like you have undercooling, you have shielding, and whatsoever. But we ran out of time doing the opposite. The idea to take a DTA and create an enthalpy curve from it was intriguing, but we ran out of time doing that.
Can I answer a question? Yeah. Thank you, Ursula, for your question. Nice to see you, and sorry for playing with your slide with that Calfat pyramid you provided. Yeah, I understand that these possibilities already included in FactSage and Thermocalc to generate the thermal effect as a function of temperature, at least the cooling curves, right? And at least I didn't explore it myself, but it's already there. The question to make it more accessible for thermal analysis users, because you cannot expect any Calfat user to learn ab initio computation, but they benefit greatly. Same like for thermal analysis, regular thermal analysis user, it's hard to expect them to buy and learn FactSage or Thermocalc just to help to interpret data for thermal analysis.
No,
there may be some open Calfat features that could be used for that.
No. It has nothing to do with the Calfat software. Basically, what I was thinking of to have you make a DTA analysis, you get your curve or your recording of from the DTA instrument, and then you take your software and it takes the instrument parameters and reverses that to extract the enthalpy change during the course of the DTA run. That in turn would be valuable input for Calfat. It has nothing to do with Calfat at all at the current point.
Yeah, that's what we do. That's what we do, of course, for enthalpies of transition and fusion, and for the heat capacity, we can do the heat capacity when there is no weight loss for that range, right? Yeah, so this data, I believe, that provided from thermal analysis to Calfat already. And I've seen several papers. Actually, we talked to Susanna Price about this, and she gave me several papers where people used to correlate data from Thermocalc on metal alloys with the real thermal analysis curves. So it's of course possible and doable. Yeah, I just surprised that it's not being used much more widely, given that there are already commercial incentives to do this. You don't need government funding for that, right? Because Nature, of course, a private company with a big market, and so I just hope that maybe there will be some communication on the level of companies just to tap into that source. Did I answer that, or?
Yes, but I think we should postpone.
Yeah, we can talk together. I can log in to Gather Town after we can discuss more.
A wide audience.
Yeah, absolutely. Yeah, I would love to.
Okay, so the next question we have in the Q&A session is from Philip Spencer, and it looks like he's been promoted. Philip, are you able to share your camera and then ask your question? Oh, I think you're muted.
Can you hear me now?
Yes.
Okay. No, it was directed to Alex, but I understand she's not online. Is that right? Perhaps Axel.
No, I'm here, but my video is not working on.
No, Alex.
Another Alex.
Alex.
Another Alex. Okay.
But maybe Axel is the one to answer the question. I don't know.
Just because I have the same letter doesn't mean.
It's a good excuse to switch to you. That's right. Yeah.
I think Sergey might be better, but I can give it a try.
Okay. Well, it's one which other people will have an opinion about anyway. And Alex, with her tremendous reputation with experimental work, is one of the world's top experimentalists in calorimetry and so on. And she is working closely with ab initio people. I wondered whether she has an opinion whether her experiments are going to be replaced by ab initio calculations in the foreseeable future. And if not, or where, her experimental measurements are going to be most required by the ab initio theoreticians. Come on, I'm waiting.
Well, I can't imagine what she's thinking, but I think I cannot claim that we will, replace all experiments. Nature has always ways to throw curveballs at us, and there are always, complex phenomenon. But I can tell you though, the number of things we can do is increasing, and there are things that when I started my PhD, I never thought I would see in my lifetime would be doable, and are now just routinely done. So I think a lot of it is not whether we can do it, is whether the economics of it is worth it. We are starting to be in a regime where there are some quantities that are cheaper, just in terms of person, time, equipment, that are cheaper to get computationally, and that tipping point is constantly moving, and we're gaining some traction. But I think even though computers are getting exponentially faster, problems tend to also get exponentially faster as you want to refine them. So, going from zero temperature to finite temperature is exponentially more complex. And so even though we had an exponential increase in complexity or the computing power available, the advances we made are much less spectacular than that. But they do happen. And I think over time, we will overtake the world, but not really. But, and as I said in my conclusion, there are things that are still, very, very difficult. I mean, if you think about just the extreme case that I can think of is a Sharpie test, right? Where you want to check the toughness of a material, mechanical property. It's a trivial experiment, cheap, very easy. It's absolutely impossible to model this with any reasonable accuracy at this time, right? So you have to really pick. I think at any given time in the history of science, there will be a threshold where things are better done experimentally or computationally, and that threshold is just moving all the time.
I'm pleased to hear that. I was interested to hear you say the calculations are very expensive too. Do they compete with experimental work in cost?
I think it depends on what. I can give you an example that maybe Kijan can jump on too as well. I mean, computing a melting point, you would think is something that experimentally is very easy to do. But what we've learned actually when we ask experimentalists, they often tell us, well, it's not that easy when it's such a high temperature. And then, when he started working on that, and eventually we got something working that worked pretty well. Now, it does take a lot of computer time, but it doesn't take any human time. He has automated that so well that, he can run it in the background for a few months and he gets the answer. In the meantime, it takes a long time for an experimentalist to purchase the material, to set up everything, to get beam time, whatever, all the things that you have to do to get it to work. And so, there are different trade-offs, and surprisingly, sometimes we come out well ahead because it's so well automated and it's not our time, it's the computer's time.
Thank you for your answer.
If I can add to this, absolutely, the trend is there, right? Like now, no one is doing gas thermodynamics, right? Because computations just do it more accurately and
very good example, yes.
Yeah, but I just want to bring one thing that in Davis.
Oh, finally, hello, can you hear me now?
Oh yes, Alex, here you are. Yeah, I'm just answering the question if our measurements will get to be outdated or replaced by computation.
Yeah.
So there is a there is of course very great progress on calculation of formation enthalpies, and I recently looked in the materials project calculations even at 0K, and it's amazing, you know, like there was so much work, for example, by many groups to get formation enthalpy of hafnium oxide with you know, very painful experiments, and I see that from materials project you know, some of the formation enthalpy is pretty good, and but there are areas where there is a still long way for computations, like for surface energies, because one of the we didn't talk about this, but many measurements Alex did since 20 years ago were on the surface energies, and so this solution calorimetry, for example, yield average surface energy of given material, right? And with computations, you can calculate energy of a particular surface, but to predict which surfaces are in real material, right?
And the reverse problem is considerably more expensive. You're right. Yes.
Yeah, yeah. So this direction is actually very. It's only emerging, right? And of course, CalFAT which involves surface and interface energies, are only starting to develop, right? Yeah. So I think that there is a long.
Now, to be fair, another competitor to computation will also be robots. You could imagine automating experimental processes as well, right? In a different way. So that could be. We're not even talking about this right now, but it could become something fairly significant in the future.
But I think there's another really important thing, and that is that when you do can you hear me?
Yeah, absolutely.
Yes.
That when you do computations, you know, if you can compute something that has been measured and it agrees, then as an experimentalist, but probably the computational people as well, feel more confident that their whole method, their whole parameterization, everything that goes into it is reasonably accurate. And then you can calculate things that are much harder to measure. So for example, if we've measured some heats of fusion and you're okay on them, and then you calculate some high temperature heat capacities, there's more hope, I think, that the computations are in fact accurate if they've been vetted on one or another measurement. And then the next thing, which is equally important, is perhaps more for CalFAT type computations than for the ab initio, is CalFAT ought to be able to tell the experimentalist where more data are needed, where the free energies are, you know, the slopes are really shallow, everything's crossing over. You don't want to waste your time doing experiments on parts of phase space that are already well constrained and where small differences in computational methods don't give you big differences. But when you look at multi-component compositional space, you can, you know, you have to close the loop where the computational people say, hey, here is where it's worthwhile to get more data.
Yeah.
So no, we don't intend to go out of business.
I want to make a comment on this one. I think it's very important. I want to point out that the DOE actually issued a big program, a few multi-million dollars for individual projects just the last month. The first sentence of that FOA is, today, at the moment, what the computational prediction still cannot fully predict the macroscopic properties of material by experiments. Okay, that's actually the first sentence of that big program. So I wrote a proposal for that, and we haven't get funding. I don't know whether they get funded or not, but interesting that. So the question is why the computation at the moment cannot predict these macroscopic properties. But my understanding is that the reason is because when you experiment, you measure a lot of things together. But when it's computation, you have one specific configuration. By the nature, when you do the measurements, is multi-configuration combined together. Okay, I think that is actually, in my opinion, is one of the largest challenge. Now, of course, you ask how many configurations experiments measure? Well, I think somebody did an estimation before. It's 10 to the 5th order. Okay, so that means you do one experiment at high temperature, you measure like 10 to the 5th order configurations. Then the calculation, you do one configuration, or maybe you do more than one. Okay, so to bridge these two together, that's, I think, it's really the computation, the challenge for the computation to do in the next 10, 20 years.
So this topic of conversation is absolutely fascinating, but we've had quite a few questions come in. So what I would suggest is maybe this particular line we can table for GatherTown. And I do want to acknowledge Natalie and give her an opportunity now to ask her question to our distinguished speakers here. Natalie?
Yes, do you hear me?
Yes.
Yes.
Okay, so could Axel share the view where he has a phase diagram for the nickel rhenium, please?
Mhm.
Can you show your slide?
Nickel rhenium.
Nickel rhenium in the first part.
Natalia, you can show your video now. Your promoted co-host can show your video.
Whenever.
Yes, I just have to open up my my talk. Hold on. Was not ready to open it. Nickel rhenium. Nickel
Yeah.
rhenium. All right. Okay. And then I will share my screen.
Please.
Hold on. Yes. Yes. Okay. So do you see my screen now? Whoop.
Yes.
Sorry. There we go. Here. Okay. Yes.
Thank you. So I have actually two questions. One is, could you explain me how you managed to get FCC stable for the rhenium at high temperature?
Oh,
And
this is an artifact. I mean, actually, the energy difference between HCP and FCC is extremely small. And in this project, we were really looking at the low temperature behavior because we wanted to rule in or rule out the ground state. And so at high temperature, if you don't do thermal expansion, the HCP and FCC cross a little bit, and that's not, it's obviously not physical. We didn't spend too much time on that part because it's known that rhenium is just HCP all the way, right? So it's not something, it's not a prediction that we had to, really look at.
so is it for that for that reason that you have such a bad solubility curves?
No, the solubility. What do you mean bad? That the
your solubilities are too high.
That is
both
true,
in
yes.
rhenium.
We are a bit perplexed by that, especially on the rhenium side. That it is very. If I had to find really a reason why this is, I would suspect that has to do with the simplified modeling of the short range order in that alloy. And so that is what I would expect is the reason. And again, this is taken from a paper that actually looks at a way to rule in or rule out certain ordered phase that are predicted by other groups and do it in a fast way. So, obviously, if we did something like a cluster expansion, this would probably be a lot better. It's a different trade-off between accuracy and computer time that we spend. I agree with you. It's a bit surprising. Now, it's actually kind of strange that some experiments did find such large solubility, and it's very uncanny that it's almost on top of our line. And I would not claim that it is true that maybe it's fortuitous, but it's so very suggestive that it seems that maybe those free energies are so close to each other that it's very easy to overshoot, both in experiment and in computations. So there could be something real there. I think it would deserve much more accurate calculation to really settle this problem, settle this question. But anyway, so this is what I have to say just about this particular problem.
May I have just a very little one more? Why 3 lattice for sigma, and which one do you merge to make only 3?
I'm sorry.
On a few slides before, on the description of the
for
sigma
the phase, why there are three?
you had only 3 sublattices. Why and
You
which
know,
ones?
I know that crystallographically there are 5 of them, but and we could do 5 if we wanted to. That's not a very big problem. The reason we did only a version of the S2S that has only 3 is that if you do very high number of components, there's really an explosion in terms of configurational complexity. If you have only 3 sublattices, it's very manageable to enumerate all the n members. If you use the 5, then it's very it's just the number of computation explodes so much that you just don't get an answer in any reasonable amount of time. It's better to have an answer that's reasonably accurate than to have the perfect answer in an infinite time almost.
But the question
is the which you group is that some of these sublattices have different coordination. And actually, I didn't come up with that. There are known papers that I've been doing this for years that have modeled the sigma phase with only 3 sublattices rather than 5, just based on the coordination of each sublattice. So you group the sublattices that have the same coordination, and that's how you save in the number of sublattices.
But both by calculation and experimentally, it has been shown that depending on the systems, actually the sublattices that are more getting that should be merged together are not the same depending on the system. So that's that's something that calculation can bring, that you do not give the chance to get from this oversimplification, whatever the system, the same.
Well, I am not the first one to make this simplification. I mean, I think that that is relatively commonly made, and the element that I have regrouped per lattice are those elements that have that prefer to adopt certain configurations. So the things that are placed on the same sublattices are elements that like a certain coordination, and they're placed on the sublattice that has that coordination. So I think that there's a lot of, there's some reasonable physics to narrow down the possibilities. And again, you have to realize this was part of a work where we looked at a 4-component system where there were a lot of phases, and the sigma phase was a tiny sliver somewhere that was there, and it was not really our main worry in the project. So we had to be efficient, and so that was a very using a 3 sublattice model, which, as I said, has been done before, was it's a time saver, and it's a compromise between the amount of time you spend on computers and the possibility of getting an answer that is quite reasonable at a reasonable amount of time.
Thank you for your answers.
Natalie, I'm afraid we do have to cut this off. I do encourage.
I say thank you,
okay.
And thank you to all the speakers of this night.
Absolutely. Thank you, Natalie. I did want to give JC an opportunity to ask his question to this group, because I think it will also be an interesting topic for discussion as well. JC, please go ahead.
Yeah, my question is for Axel about you predicted the highest melting point, the solid, right? The couple hafnium couple.
It's mostly for Kijan. He's the one who did most of the hard work there, but I'm happy to answer too.
I mean, do we have a way to predict what's the highest melting point, the oxide? Way.
So just limiting ourselves to oxide, what would be the highest melting point?
Yes.
Well, Kijan, we could just try. Let's start with the highest known, hafnium, zirconium, and mix them up. I mean, that would be my first guess. I don't think if you mix hafnium, zirconium, you're going to get any better than the hafnium, because they are the same, same valence. So probably it's not going to make a difference. What had guided us for the other one, the hafnium, carbonitrate, was we thought by having nitrogen in there, it would change valence enough so that you would insert vacancies, and the vacancies could give us some entropy, and the entropy would stabilize the solid. And there are no vacancies in the liquid, so that means it's something that you gain only in the solid, and that might increase the temperature. It didn't turn out to be the full explanation, but it is part of it. So I wonder if there would be something we could do on the hafnium oxide where we could force vacancies to form so that we would get extra entropy.
Axel, change it to thorium oxide.
Thorium. Thorium is
Forget
too
hafnium.
expensive.
No, I mean, highest melting. I mean, thorium is champion, so you need to.
Champion, yeah, okay, yeah, I guess it was out of my mind. It's really expensive though, right?
Yeah, but if directly answering the question, highest melting. So thorium is there now highest melting. So the way is maybe
thorium. I'm sorry. Yes, you're right. You have that all in mind. I didn't, but yeah, I guess that the people who do turbine blades prefer to use less expensive elements, but yeah, I mean, I think my guess would be to take something that's already known to be high, and then introduce something that would maybe max out the entropy. Because I mean, the bonding, you basically max it out by having stoichiometric compounds, right? There's nothing much you can do. You just count the number of valence electrons, put them into the bonding orbital, and these oxide have maxed that out already. So I don't think you can do much more in terms of just chemistry. You can do it in terms of entropy maybe, and that would be, you know, by mixing things that forces constitutional vacancies, maybe that would be a way to increase it a little. I don't know. Kijan, do you have any idea?
I just want to say we have the second step. That is, if we have an idea of material in our mind, we have the tool to compute it or measure it in experiment. What we don't have is the intuition part of what could be that material. So it's maybe out of the field of computational material science, but there are some ways to maybe to build a model to predict which combination of elements could be the best. But still, I agree with JC. At this moment, we don't have this model.
Yeah, it is an inverse problem, right? We can test ideas that we have, but there's no reverse problem that's programmed already.
I mean, what I find difficult to think of for the oxides game is some sort of mechanism that creates vacancies or other sources of disorder in the solid, but not in the liquid. There may be some special cases, as you're saying, for metals. But for oxides, because all of the defects are strongly charge coupled to get charge balance, I find it hard to imagine some defect mechanism that would operate in the solid but not in the liquid to increase the entropy of the solid. I don't know, maybe I don't have enough imagination.
No.
I think along the same line of high melting point material, we would be very interested in look at what is the highest melting point aluminides. Alumina is not a 1-to-1 ratio like any aluminum containing compound that has more than 20% atomic percent aluminum. Okay, so what is the highest melting point compound of that?
Are you talking about metallic, or are you talking about oxides?
I'm talking about the metallic, just like or intermetallic, right? You know, something that contains 20%, more than 20 atomic percent aluminum that has the highest melting point. And we would be very interested to see that that alloy compound. Okay, so there are a lot of interesting things if the DFT and other tools can be used to help us guide us the selection of materials like that. That would be very interesting.
Excellent. So this has been a
Can I add one comment,
Q&A.
Richard? Can I add one
Of
comment?
course.
Thank you. I think to answer Jason's question, there was one recent paper by Stefano's group at Duke. It's a combination of the machine learning and the computation and then the experiment. That iteration is what he found. And he had a paper, he talked about high entropy oxides, high entropy carbon nitrides. And then for the machine learning, you do a prediction. Actually, he showed a couple of examples with predictions by including entropy. It has very good opportunities to predict the high melting material.
I will check it out. Thanks.
All right, excellent. So this is an excellent discussion, and I don't want to stop the discussion. So I encourage all of you, as the session closes, to log on to the Gather Town, where the discussion can continue indefinitely. And I also want to once again thank all of our speakers, all of our attendees and question askers for all of your great participation in all of this, for a really excellent session. And at this point, I do want to throw it back over to Yuzong for any announcements and also to formally close the session.
Yeah, okay. Yeah, thank you very much. So thank you, everyone. So as Richard mentioned, so the next item will be this Gather Town. And I think I already mentioned about the schedule for the next session, which will happen in next week. So one day before that, I will send you if there's any update. So please keep track of your, the email announcement. Yeah, thank you, everyone. Yeah, so have a good day. Enjoy the Gather Town activity after this. Yeah.